Well, it's a great pleasure and honor to be here to help your university celebrate its 50 years of existence. As Martin said, I've been here many times and always enjoyed it. And thanks to Martin for the invitation. And he and I have had many conversations over the years from which I've learned a lot. So let me give you a little bit of background to this talk, because I'm going to be addressing the overall topic of this workshop somewhat indirectly. So as Martin mentioned, for quite a long time I've been interested in the interaction between computational methods and how science is done. And when I wrote the 2004 book, back then I was mostly interested in traditional computational methods. But now, as you know, in the last decade, since roughly 2008, there's been an explosion of work in machine learning, some of which is now finding its way into some of the more sophisticated sciences. And one of the great problems of this work in machine learning is the difficulty of understanding how some of these very successful methods are actually doing what they're doing and being successful. And so there's an area called explainable AI, which is in its infancy, and it's directed towards the question of the extent to which we can understand these methods. Now, there are a few constraints on what I'm going to be doing today. So there are a lot of ethical issues involved with current artificial intelligence. They're all very important, but that's not what I'm interested in. I'm interested in the epistemology of these methods. And the first half of my talk is going to be to convince you that the epistemology of machine learning, big data, neural nets is very different from the kind of modeling that we're all familiar with in the more traditional approach to the sense. So let me start out with just some basic philosophical distinctions. All right. So the oldest one is a distinction between what I think of as traditional empiricism, which goes all the way back to Aristotle, was there in the 17th, 18th century, and the so-called British empiricist was revived by the Vienna Circle and German-speaking philosophers in the 1920s and subsequently, and continued on until the 1980s. And the contrast between that kind of empiricism and the problem of how we can come to justifiably argue that unobservables exist, occupy philosophers for a long time. I think that that particular debate is just dead and gone. Traditional empiricism is embarrassing to teach in undergraduate classes. Why can't we believe in viruses, sir? Well, you should. So you need to switch to something more general, which one can call generalized empiricism. And when you get there, what you have to do is not become a comprehensive realist about what is at that point no longer observable, but a more selective approach. That's very interesting, but once we get to artificial intelligence and machine learning, I think the central problem is what of those things that we're extracting from the data constitute genuine objective features of the data, and which of them are artifacts. So that's the focus that I'm going to be looking at. But again, here are the restrictions. It's very, very hard to keep up with the current flow of information. This is an explosive field. New important results are coming out every couple of months. And what I'm going to try and do is just give you a flavor in one area of how one can approach this issue of understanding the way that these machines represent the world to themselves. Lots of different architectures, lots of different machine learning methods. I'm just going to focus on one. It's very widely used. If you know what these are, they're feed-forward convolutional neural nets using a learning process called backpropagation, and importantly, they use what's called supervised learning, and I'll explain what that is in a minute. And because of the relatively accessible understanding of these things. I'm going to focus on image recognition. That's somewhat typical of other methods, but it is a restriction. All right, so here's a basic form of convolutional neural net. So you start out here with an image of something. Is this two-dimensional image of a car. There are input sensors here, so this is a pixelated image. This is scanned into the input of the neural net. Here's the convolutional part. There's a filter which scans over the input of these successively. And the filter here is designed to pick out particular features. And so in this particular example, when it's focused on the bit of the image up here, and the filter is designed to detect horizontal line segments, then it will pass through a signal to the next part of the network. If it's scanning here and the filter is a left diagonal recognition filter, then it will pass that through, otherwise it won't. Redos, these are just non-linear transformation devices. If the signal is not strong enough, it will block it. If it is strong enough, it gives you a linear response. Okay, next thing. The information from these successive scans is then in certain kind of regions here pooled into an aggregated information here in the next layer. Right? And then the process takes on similar iterative process. You go through convolution, redo, and pooling again. Number of layers varies. Deep neural nets probably start around 5 layers, then go up to 1,000. That's where some of the different architectures come in. Then you get up here to the final phase in which, unlike these areas which are sparsely connected, this is fully connected. And then here you've got what's called a softmax classifier, which converts the information at this last level into a probability distribution. And the probability distribution is over a classification set of categories. It goes from cars, trucks, vans. And what you're after is, what does the softmax classifier give you as the most probable classification in that range? And that's the one that the neural net is going to identify as being the object that's given to it in the image. So that's a basic setup. If you're familiar with the connectionist literature from back that started in the mid-1980s, just a quick thing. Convolutional neural nets are not just bigger connectionist devices, and here's 3 ways in which they differ. Deep neural nets are exponentially more efficient in a number of applications than shallow neural nets, where shallow neural nets only have one intermediate layer. I've already pointed out that there are these specific devices like ReLU units and convolutional filters, which were not present in the connectionist area. And convolutional neural nets are generally sparsely connected in the earlier stages. They only get fully connected in the last layer. If you want a nice survey of this, here's an article by Cameron Butler on that. Okay, so one of the restrictions is, as mentioned there, we're going to be talking about classification. Classification is a recognized part of some areas of science. Even if you're, for example, working at the Large Hadron Collider, you're interested in what classification category this particular signal is going to be fitted into. Now, I mentioned supervised learning. Now, supervised learning is a process in which the deep neural net is trained by using part of the data set, and it originally starts out as having a fairly low level of accuracy, and the backpropagation technique uses, in the image recognition case, humanly labeled results, which would, for example, in the case that I just gave you, that input image will be labeled by a human as a car, right? And if the neural net initial output gets it wrong, the feedback device will correct the weights in the inner layers of the network. It will do it again, and then often hundreds of thousands of training examples, but they're all constrained by our prior decisions as to what category the initial images go into. So this is an important human input to deep neural net learnings, and we'll see why that's important in a minute. Now, one of the intriguing things about image classification with deep neural nets is that, on the one hand, they're enormously successful. They have upwards of 95% success with a wide variety of images when they've been properly trained. But on the other hand, they're what's called brittle. They suffer what to humans seem to be surprising mistakes on certain kinds of images. And I want to focus on two kinds here. Here's the first kind. And this is something that one can understand why it's making mistakes. So if you have an image of a monkey and superimposed on it is a motorcycle, a properly trained neural network, which if it's given the monkey, is going to immediately classify that correctly. When you have that composite image, the monkey is identified as a human. And you can understand why that is, because when you have motorcycles and there's a mammal in it, that mammal is almost always human. So that's why the deep neural net will make a mistake there. In this second issue with this a bicycle, here's a monkey identified as a human, but if you look up here, I don't know if you can see this, the boxes are the things that the machine is focusing on in the image. That part of the handlebar of the bicycle, the most probable classification for that by the deep neural net is as a bird. Why is that? Well, you can see the background here is a jungle, there's a monkey in it. You certainly don't expect a bicycle in there. The training examples would, if it probably included, in the jungle with monkeys, a bird up there. So what it does, monkeys identified as a human, and that bit of the bicycle as a bird. This last one is also interesting. The monkeys, as usual, identified as a human, but it classifies the guitar as a bird. Now, that's a weird mistake, right? And again, it's almost certainly because the context in which the training took place was on images in which you certainly don't find guitars in jungles, and it picked with, I don't know if you can see what the probability is there. It's about 0.3, which is not very high, but it's certainly the highest level of the classification. So that's one kind of misidentification, but we can sort of understand why that kind of thing is going to happen. Here are more interesting examples, and they have become a central problem in image recognition, and they're called adversarial examples. And how these go is this. You start out with a image of a panda, right? And the properly trained neural net has no problem labeling that as a panda. You then introduce what is often called noise, and this is a graphic representation of that. It's not actually noise. They are carefully crafted minor perturbations to the pixel intensities and the inner activations of the network, which to the human eye, that plus the added perturbations is the image here. And as a human being, we cannot distinguish that perturbed image from the original unperturbed image. But to the machine, this crafted perturbation that's added to the image here gets the machine to put it into a different category. Now, this is a real problem because a lot of this stuff is driven by intelligence agencies. They want to identify particular images as, well, people who are doing things that they shouldn't be doing. If you introduce this kind of perturbation, you're an adversary, it will throw it off and identify it as the kind of person who you really don't need to worry about. So aside from the theoretical problems with this, there are practical problems with adversarial images. We shouldn't be feeling so superior, though, because as we all know, human visual system is not perfect. If you're reasonably good at switching back and forth, you should be able to see at least 3 different interpretations of that image. Possibly, if you're good, you can see more than one of them at once, but that kind of thing, which again is deliberately crafted to fool the human vision system, is an indication of how even we are susceptible to problems. Now, what I'm going to do now is to give you 2 recent accounts of why those adversarial images cause problems for deep neural nets. The background to this is a couple of technical results. This is really for the mathematicians in the audience. These devices are universal function approximators. And this first one, which goes back to 1989, basically says if you take any measurable continuous function, a large enough neural net will be able to approximate that function arbitrarily closely. Measurable functions are very common. All random variables are measurable functions. So that's a good indication that one of the things that deep neural nets are doing is actually taking the input, crafting a function which will take you from the input to the output, and that's why they're so good as they are. The second one here is just a variant on that. Well, of course, deep neural nets are not, infinite limit devices. They're finite. So here's a more recent one from 2016. So if you've got number of input data points is n, that's the number of things in the training set, and the number of parameters in the network is p, that is the number of connections and the number of weights available to you, and that's very, very high dimensional. But as long as the number of parameters is bigger than the number of data points, then there's a 2-layer neural network, so that's pretty shallow. You can do it just with that, with the usual architecture that I've told you. It can represent any function whatsoever on a sample of size n in d dimensions. Right? So even in the finite case, what you've got here is a function approximator. And that's something that leads to problems. These deep neural nets are actually more powerful than we need. And the interpretation by the authors of that finite approximation theorem is given to you on this slide here. They claim that sufficiently powerful deep neural nets, which is actually most of the ones that are used in image classification now, what they're doing is basically memorizing the training set. Now, these training sets often stretch into over 1 million images. Right? But they're so powerful that what they've done is they've fitted a function to, let's say, those 1.2 million images it's been trained on, and it just memorizes each one of those things in the internal representations. And when it comes to a new image, well, most of them are sort of close enough to the ones that it's memorized, but some of them, including adversarial examples, are just a little bit too far away from that, and so it doesn't know what to do. It sort of just picks something that seems to, in terms of the function it's fitted, it's the output that it decides is warranted by the input. Now, so this is a version of overfitting, right? And of course, people in this area are well aware of this, and so that overfitting problem is countered by what are called regularization methods. Common one is dropout. During the training process, you knock out individual nodes in the network to force it to be successful on image recognition, even when it's not relying too much on a single node. So, these methods are reasonably successful, but not completely successful in terms of adversarial cases. Now, here's something that I wanted to draw your attention to. Universal function approximators are not new. Figure up on the left is Ptolemy. His famous Almagest, that was published in 150 AD, became the canonical work for astronomers between 150 AD and when Kepler came along. Even Copernicus was using the apparatus that Ptolemy had invented. And what the devices do, or one of the central devices here, is, right, this is the ancient representation of the planetary system. Here's the Earth at the center of the universe. Here's the sun going around the Earth. Here are the usual planets that they knew at the time. And the method of predicting the motions of the planets here was to put the planet Venus, for example, on a large epicycle here, together, a large deferent here, together with here just one epicycle, and the planet is moving around in the epicycle, and that's being carried around the Earth by the deferent. When you generalize that, there's no upper limit to the number of epicycles that you can put on, and this has come into the common law that you can have epicycles upon epicycles upon epicycles. Turns out that there's analogous approximation device for that. I'll just let you read that. I don't think that the ancients knew this. I mean, they certainly didn't have the mathematical apparatus to prove that approximation device. But I do wonder whether they suspected, as this astronomical calculation device became more and more successful, that they'd latched onto something that was really, really powerful. And it's so powerful that if history had gone in a different counterfactual way, we would have been in trouble. So this person on the left is Johannes Kepler. I think, in my view, at least as important as Copernicus in getting us to the modern motion of the planets. So counterfactually, imagine if Kepler, who's a very smart guy, spent 10 years calculating the motion of Mars and ended up with the hypothesis that it was an ellipse. Suppose that we'd actually just given him a laptop with the epicyclic apparatus fitted into a traditional algorithm. It would have saved 10 years of Kepler's life. He would have been able to fit an extraordinarily accurate epicyclic system to the data of Tycho Brahe, and at that point right there, boom, no more ellipses, right? The Ptolemaic system would have gone on for a lot longer. So thank goodness that Kepler did not have a laptop. All right. Okay, so that's the first hypothesis, that the reason why these adversarial examples exist is because they're fitting functions to the data. All right, so here's the second part of the talk, which is sort of more directly connected with the topic of this particular workshop. So what I want to at least suggest to you is that we've already moved in the area of traditional modeling away from the idea that humans are the ultimate epistemic authority. We would never have discovered the Higgs boson without enormous amounts of simulations and data processing. And of course, we get to decide when the 5 or 6 sigma event has occurred, but all of the really heavy lifting is done by computation, right? So I want to just suggest to you that we're beginning to move into an era in which these kind of neural net machine learning techniques are possibly things which are not only going to supplant us, but we might be able to understand to the extent that we don't lose contact with what they're doing altogether. All right. So, philosophers talk about models a lot. Here's what a traditional model looks like. Just think about a differential equation model. Those differential equation models, unless you just take them as sort of rote things you got from a textbook, are constructed from explicit assumptions, right, which may or may not apply in particular applications. When you're using differential equation models for a particular application, you're usually doing it, certainly within the physical, biological sciences that have some sort of explicit theory. Whether or not that's applicable to the case at hand is going to be constrained by the theoretical background that you're working in. The representations are also explicit, right? I mean, differential equation models are there. You know, you understand the mathematics properly. You don't need any further interpretation of the representational device. So here's just a little definition. So a representation is explicit for some agent A. That's in there because computational devices are agents, and things that are explicit for a computational device are not necessarily explicit for us and not vice versa. Right? So it's explicit for the agent you're considering with if the only thing that the agent needs in order to understand what the representation is doing and actually to use it is just trivial transformations. Right? Importantly, you also need the relevant conceptual apparatus. Right? You want to connect the differential equation up with whatever the theory is that is constraining the model. You need to have the conceptual apparatus of that theory, and obviously the mathematical concepts that are given as well. Generally speaking, with traditional models, the models are pre-interpreted. Once you've got the differential equation, you interpret it within the context of the theoretical background, and that's what you go into the application with before you start comparing it with data. All right, those are standard models. There's something, kind of device called Computational Templates, which I introduced in that 2004 book. They're different from traditional models because their primary focus is that they have to be computationally tractable, right? A lot of theoretical models are not. They're good representation devices, but their application in particular cases is difficult because you can't do the computations to get you the relevant predictions. That's something that is required of a computational template, and here are the main features of them. Again, we tend to construct the computational templates, at least back in the days of traditional algorithms. As I said, they're constrained by tractability considerations. The representations are also explicit in the days of traditional algorithms. But because these computational templates can be transferred from one scientific field to the other, they're generally speaking, mathematic or algorithmic devices which are purely syntactic, and you have to, what I call, post-interpret them. That is, you interpret them after they've been embedded in a particular disciplinary application. So that's the intermediate thing. Now, here's a suggestion for what kinds of models and representation devices are being used by convolutional neural nets. Now, this is just my view. There's lots and lots of different hypotheses about what's going on in these things. But I think there is justification for what I'm about to tell you. They're not, by their nature, constructed by humans. They're not constructed before the training period begins. They're constructed by the machine learning algorithms from the data. So they gradually emerge after often hundreds of thousands of passes through image data sets. And at the end of the training process, somewhere inside those machines, at each layer in the deep neural net, is a representation of something. And I want to call those representations models. They're obviously constrained by the data set. Here's a contact with theory-free methods. There are a lot of exaggerated claims made early on for neural nets and big data that we were going to be completely free of theory. That's insupportable in many kinds of cases. But in this situation, I think it's reasonable to think that at least for some part of what these convolutional neural nets are doing. You really don't need theory. And that makes it interesting because, right, let's go back to the function approximation view. Those are just functions, right? They're not interpreted yet. So a function is as good for a biological application as it is for an application in chemistry, as long as it's of the right kind. So these are discipline independent to a large extent. Big difference between computational templates and traditional models. Representations are implicit. And here's what it is for representation to be implicit. You require a non-trivial transformation for the agent to extract the representational content. Right? And then there's an interpretation, which often is opaque to us, that's generated in training. All right, I think in the interest of time, I'm just going to just briefly skip over this stuff. What you want out of these representations are invariances. And here's some examples. You know, invariance under rotation, translation, and scale for geometrical shapes. You rotate the triangle, it's still a triangle. You translate it, it's still a triangle. Now, here's the second interpretation of what's going on with adversarial examples. And let me try and convey this as carefully as I can, because it's a little bit tricky. So you start out, as usual, with an image set, and this is supervised learning, and the label is, from the perspective of the human, correct, right? Says, this thing here is a dog, right? And the neural net is trained, it's trained well, and with a very high degree of success, it will in fact recognize at the end of the training process that thing is a dog. Now, remember back to the panda example, you add some perturbations to this image, and what those perturbations do is to nudge the image from the classification category in the output of the neural net towards an adjacent one which human beings have labeled as a cat, right? So this is crafted. So with the perturbations, this image here, and this is the one with the perturbations added, and remember that the human eye cannot detect those perturbations, but the machine can. It's going to nudge this perturbed image here, which should be a dog, and it's going to be labeled cat, right? So that's an adversarial case. Now, you've got this set of perturbed images, right? So thousands and thousands and thousands of them. So you now take a new neural net, not the original one, a new one, and you train it on those perturbed images, which, remember, look exactly like the originals to human vision. And because the training methods are really good, and the labels have been tailored to what the original device said that object was, which in this case is a cat, it gets to learn that this image here is an image of a cat, because to the machine it metaphorically looks like a cat. Now, that's, I think, in itself interesting. But here's the really fascinating part. Now you feed that second neural network unperturbed images of dogs. So, in a certain sense, these really are images of dogs. And it turns out it's pretty good at recognizing these things, right? Not as good as the original one was on the image set, but pretty darn good, right? Certainly far better than chance. In this particular case, it does it with 0.433 probability. There are 10 classifications, so that's way above what you would expect by chance. So the question is, what's going on here, right? And here's the interpretation. What the second trained neural net is picking up on are two kinds of features in the image. And the proposers of this interpretation divide those features into two kinds, what they call robust and non-robust features. When the non-robust features, which are the things that the adversarial attacks perturb, when they're left alone, that is, they're in the original image, the machine aligns itself, it looks to the machine to be the same kind of thing as the robust features are telling it it's going to be. However, when the non-robust features are perturbed, the adversarial attack, it turns out for the machine, those are the things that it relies on in order to classify the event. So when you take that image of a dog, you perturb it, so the non-robust features are what is going to dominate for the machine. It then classifies it as a cat. So it's relying on the non-robust features with the adversarial examples. All right. Let me, Martin, how much time do I have? I'm out of time. Yeah. Okay. All right. I'm out of time. All right. So, yeah. So I certainly want to allow. So here's the central moral. What's important for these kind of devices are not classic observations that humans have, but what are called features. Things, patterns in the pixel array that the machine is picking up on. What counts as an important feature is going to vary from application to application, especially from discipline to discipline. So these things, despite the functional approach, are probably not particularly general. Across disciplines, features don't have the subject matter invariance for traditional observations, right? We rely on our visual device to take us from biology to sociology to physics and so forth. These things are not. They're subject matter specific after they've been trained, right? So the prospects for transferring models, I think, are potentially very different for these convolutional neural nets than they are for traditional models. All right. Okay, so let me skip over that, and those are the thanks to some of my co-workers, and I'll be glad to answer questions. Thank you.